Okay, learning objectives are what are the effects of deferred maintenance on energy efficiency and cooling and heating performance over time. Essentially, I'm sure as you know, the performance is going to decrease over time if maintenance is deferred, is the short answer to that, but we'll get into these things a lot deeper. The difference between corrective and condition-based maintenance versus performance-based maintenance, we're going to talk a lot about that. Corrective is essentially fixing the unit after it's not working or broken, whereas condition-based and performance-based tries to predict or catch things before they get so bad that you don't have cooling anymore. And then what are the most common inefficiencies, causes of inefficiencies in unitary operation? And from what I've seen, the two most common are corroded condenser coil fins and low refrigerant charge. And there's a bunch of other ones too we'll talk about. The required disclaimer slide. Okay, so the problem is that most unitary systems operate at a really low level of efficiency after they've been in service for a few years. They just deteriorate naturally without constant attention. And I say this from having looked at hundreds of units. You guys probably see the same thing, with units that are just let run to fail. They can continue to provide cooling because they're often oversized, for redundancy. So when the size is selected, usually an extra 50% or even twice what the load is. So let's say you have a package unit that's got two compressor circuits. It's sized so that if one compressor fails, the second compressor maybe can't take the whole load, but can at least keep people from really screaming. So what that causes is as the unit loses efficiency over time, say the condenser coils corrode, things come out of adjustment, it's not really noticed. The occupants don't notice because there's enough extra capacity to make up for it. And the service techs don't notice because they're not really trained. It's not really part of their service protocol to really check the performance. I mean, as long as the occupants are cool and the system is working, that's usually good enough. And on top of that, from what I've seen, HVAC O&M shops and service techs are really stretched very thin and barely able to keep up even with maintenance. And it just ends up in this cycle, this perpetuating cycle where you have units that the maintenance is being deferred, they fail, then it's an emergency replacement, which really limits the choice of what equipment can be installed. This has to be something that's readily available. And then again, that unit also deteriorates quickly and end up chasing your tail. It's kind of a hard thing to get out of without a boost of resources, to break the cycle. And that's definitely an issue with implementing performance-based maintenance is even if you understand how it works and you know what you're trying to do, and probably you're already in your situation, if you are doing deferred maintenance, you probably want to and understand why it's better to do some sort of preventive maintenance, but you just don't have the resources, unfortunately. So the other, in addition to the condenser coil corrosion and low charge, here's a bunch of other things. Refrigerant charge valve coil, a failed or slow condenser fan motor. That's a common thing when maybe a unit has 2 or 3 fan motors that just one of them isn't working, or maybe it's turning, but it's turning very slowly. The unit can still function like that, but it's going to be much less efficient. Maybe a blade missing off the fan. The TXV superheat setting is awfully really high, too high. Cabinets get rusty, air leakage. The outdoor air damper could be stuck open, clogged filters, contaminated refrigerant. But even with this kind of stuff, again, if you have an oversized unit, it could still provide adequate cooling. Maybe the humidity levels will be a little high. Maybe it'll be in the upper 70s and people won't be super happy, but it isn't going to be an emergency and it might not get attention. So I'm going to break this up into 3 parts. The first part, I'm going to talk about the types of maintenance, emergency maintenance, corrective, condition-based, performance-based. In the second part, I'm going to talk about performance-based maintenance specifically, just kind of walk through how it works. And then part 3 is a case study of where we did a pilot at Naval Air Station Key West with the technicians there and the results of that. So as part of the performance-based maintenance program, technician training is a big thing. I mean, usually we spend 2 full days with the technicians, maybe a classroom day or a classroom morning, and then a field day at units, and then another full day at the units. So these slides that are in blue here that I'm showing you are actually part of the training program for the technicians before we get into it. So first we talk about the difference between preventive maintenance and corrective maintenance, just sort of give a basis of where we are. But the idea behind preventive maintenance is to recognize a failure that is about to occur and do something about it before it fails. And corrective maintenance is maintenance after a failure has occurred. You know, again, this is part of the training program. That's me back there with the hat on. Okay, this really kind of encapsulates this slide, this curve, the PF curve. This is really something to remember here. So this is the performance of the unit over time. And the yellow line, you can see over time it drops down. And this is actually what happens. We've taken a lot of data on package units for years and years. At point P is the point where you could potentially take some performance readings or measurements and recognize that the performance of the unit has declined and potentially do something about it to get it back into a smooth running condition. Between that, then you have an impending failure, and at point F is where you have some sort of functional failure. And then that is the time where you would do corrective maintenance. And then finally it reaches its end of life. So the idea is to try to push things back on this curve, go towards the left, and try to recognize something going wrong before it's too late. Condition-based maintenance is going to be somewhere right in the middle of that curve, where you have some clues or some evidence that a failure is imminent. Performance-based maintenance, we're trying to go all the way back to that point P and use measurements to indicate that there might be a failure. Failure with performance-based is defined a little differently. We've kind of raised the bar. It's not that we just want the unit to work. We want it to work optimally. You know, we want it to work as good as that can work in the condition that it's in. The reason for that is, first of all, it uses less electricity and energy, is less likely to fail, and it'll increase the lifespan of the unit. So performance-based is a type of condition. It's a type of condition-based maintenance with a little bit of predictive maintenance involved in it. This kind of just lays out the different kind of maintenance to give you a map of where we're at. So corrective maintenance, run to fail, only restores after it fails. And this is usually because of deferred maintenance or just inadequate resources to be able to really stay on top of things. I'm not sure that all corrective maintenance assumes that failure is acceptable, but you know, apparently it is, because that is like the normal way a lot of facilities run, is they just run to fail. There's an emergency, they get a new unit, put it in, back in there. And again, I recognize that most of us know that's not the way that we want to run things. And it's just difficult to get the resources. So performance-based maintenance, the advantage there is that you can show an actual return. You can say, okay, this is going to save energy, electrical energy, reduce energy costs, not much, but enough to just pay for the extra time and parts to keep these units operating in peak condition. It really only takes maybe two technicians, about 4 hours at a unit once a year to implement it. It's sort of like a very intensive annual PM. And you know, 4 hours, 2 technicians, that is still a bit of money. But from what we found, it does improve the performance of the unit enough to pay for itself. Okay, so for condition-based maintenance, sometimes it's obvious that the unit is having issues like this poor thing here. And sometimes it's not. I mean, a lot of units you can walk up to them and they look pretty decent. But when you put the meters on them and look at the performance, you see that it's really bad. Okay, so for part 2, parameters. Hey, I kind of want to see where we're at in this room just so I know how to tailor what I'm saying. Are any of you able to actually implement some sort of predictive or condition-based maintenance, or are most of us struggling with deferred maintenance and run to failure? So if you are one of the lucky ones that can actually do predictive and condition-based maintenance, can you raise your hand so we can see? Oh, that's great. All right. That's fantastic. I guess I see the, because we do consulting work, we usually don't get called unless there's a problem. So from my perspective of the world, everything is terrible. But then, people that are doing great, they have no reason to call us. So that's really good to see. Really good. Boy, I mean, that's fantastic. Yeah. Yeah, she's asking what components do you run to failure? What is run to fail? VAV boxes? I mean, fan coil units. Yeah, I mean, some things, if there's not a return, it's hard to justify the extra effort. Yeah, especially if it's a smaller unit. Absolutely. No, I agree with that. To do performance-based maintenance, we found that not only do the units need to have a pretty good size, average 10, 12, 15 tons, there also has to be a lot of them in the program, 40 or 50 of them. I mean, if you only have 2 or 3, you start to wonder, because you got to spend the time on the equipment and the technician training. So if you don't have a good population of units, again, it might not be worth it. Okay, so condition-based maintenance, taking one step ahead, like I was showing on that curve, is performance-based. And so what we're looking for is physical evidence of performance loss rather than physical evidence of an impending failure. So we're trying to catch it even a little sooner, take some targeted action, and then from that get reduced electrical cost, reduced chance of an emergency repair, increased lifespan. So HVAC performance is defined by 3 bottom line parameters. I mean, you want cooling. How much cooling is the unit delivering? That's the purpose of the unit, is to provide cooling. So you want to know how much are you getting, and how does that compare with what it's rated for? And how does it compare what it was doing when it was new or 2 years ago? The second thing is the electric power demand, because that's what it costs to run the unit. So you want to know, is it using more power than it did years ago, or is the efficiency less than it was when it was new? That efficiency is the ratio of the amount of cooling or heating delivered to the power, which is EER, which I'm sure you're familiar with for unitary equipment. Okay, so that's the technical part. Here's the management part, and this is really more of a challenge, I think. There's these 4 keys to getting a PBM program implemented. First is sort of administrative and actually formally tasking the technicians to do PBM. What we found in training technicians is this is really not the way they usually work, and it's not the way a lot of them are trained. They really focus on coming up to a unit that's broken or operating really poorly, quickly figuring out what's wrong with it, fixing it, and then moving on. They're not really trained in trying to appraise the performance of a unit and optimize or tune it. They really like the idea of it. Believe me, they're definitely very excited to be able to do that. But most of the time, they don't have the time and resources to do it. Another challenge is for management to fit performance-based maintenance into the existing O&M workflow. So rather than just piggyback a whole nother program onto what you already have, it's good to take a look at your O&M and your PMs and maybe adjust them or add things to them or add things to the annual PM to bring them up to the level of performance-based maintenance. Training of the technicians, of course, like I was saying, is really important. Okay, so I'm just going to go through kind of how the performance-based maintenance works at a really nuts and bolts component level to give you a feel for what it does. So this is our basic unitary split system or package system, the components inside. And we've got our evaporator coil where the cooling takes place, our refrigerant goes to the compressor, and then from the compressor, it goes to the condenser coil where the heat is rejected to the outdoors, and then the liquid from the condenser coil goes to the expansion valve where the pressure is reduced, the temperature is reduced, and then the cycle continues. So performance-based maintenance is getting really deep into the root of this to try to determine exactly what values are not where they should be. So just taking the next step in there, this is what the condition of the refrigerant usually is, or I think almost has to be, yes. So we've got from the evaporator coil a cool vapor, exiting the compressor is a hot gas, then exiting the condenser coil is a warm liquid, and then you get your cold mixture. So if this is as far as you went, and you put your hand on the tubing, you would say, okay, this unit's working, and you could be done right there. But if you're trying to optimize the performance, there's ranges or target values that should be coming up. Here it is. That really give the best performance. So you can measure these things and see where you're at compared to what would be optimal and make adjustments. For example, if the vapor, the cool vapor leaving the evaporating coil, the superheat is 5 degrees to maybe 10 degrees is what you want for best performance, and you measure it and it's 20 degrees, the unit's still going to work at 20 degrees, but it's not going to work really great. So you would adjust the expansion valve, assuming it's an adjustable expansion valve, to try to get that down to about 5 degrees. And when you do that, usually the hot gas temperature is going to decrease too, from maybe 150, 160 down to 130-ish. Okay, so let's see what else we got. Warm liquid, subcooling 10 degrees. So if you see your subcooling isn't 10 degrees, maybe it's only 2 degrees, that tells you you've got something wrong with your condenser, that it's fouled, needs cleaning, maybe the fan not turning as fast as it should be. Anyway, some investigation there. And then along with the refrigerant temperatures that you're looking for and refrigerant deltas, there's air temperatures and deltas that are sort of optimal. And again, these aren't like, hard, like the condenser split, I put 10 degrees, but if it's 8 degrees or 12 degrees, it doesn't be exactly that. The thing is, if your condenser split is like 15 or 20 degrees, then you've got a real issue. And then supply air, coil delta T is another good indicator there, especially in this part of the country where it's humid. You want a good solid 20 degrees on your coil. And I know that technicians usually, if there's 15 or 20, they say, hey, it's working. And it's true, at 15 degrees, it'll still provide cooling, but it won't provide much dehumidification. And it does indicate that somewhere in the system, something's not optimal. Okay, the case study. All right, this is a implementation, a 1-year pilot. We did at Naval Air Station Key West with the technicians on site there. This was the 4th pilot that we did with DoD. The first 3 pilots we did were at Cape Canaveral Space Force Station, right along the coast here, Marine Corps Air Station Beaufort, and Fort Irwin National Training Center out in California. Those all went really well. We were able to show definite improvement in the performance of the unit and savings. But the DoD said, okay, well, great, you can send your technicians and your engineers out there from your company that know all about this stuff and they can get this to happen. And you're like, well, yeah, right. So they're like, we want you to do it with our technicians. We want you to just give them 2 days of training and see if they can pull it off. So that's what we did. So we've got, these are the guys here, and these are all really experienced guys. And they, at first they were really uncomfortable with it because it's not what they usually do. But they really do like the idea of it and took a lot of interest. And at the end, I've got some comments from these guys. So what we had was, I believe we started with 30 units on the base, and we did a couple of days of training, but then after that just set them loose, and they went around to all these units with the diagnostic analyzer and the training they got, and tried to tune them, optimize their performance. First we did a baseline measurement where they measured the efficiency, power consumption, the cooling capacity of the unit, and then they did the service actions that would target the issues that were uncovered. I mean, a simple example would be if it needed more refrigerant, we add refrigerant charge. Or if the TXV needed adjustment, that was done. And this is actually really key to make it work economically, is to only do the targeted service, because if you go in and do every possible thing to the unit and it only needs 2 out of those 5 or 10 things, then your technicians have spent a lot of time. And that's really the thing here, is to try to keep this down to about a 4-hour PM, which might be enough to replace a fan motor, adjust the refrigerant charge. They can't really go through a whole unit, which might take a whole day. They could do it, but I don't see where it would be worth their time to do that. So you really want to focus in on exactly what each unit needs. And that's where the diagnostic analyzer comes in. So this is a prototype that we developed. And what it does is measures the cooling capacity or heating capacity, the power consumption, and the efficiency level. And then it has diagnostics built into it, sort of like a really basic AI, where it looks at all the different combinations of temperatures and humidities and compares them to what would be optimal in those particular conditions. And then it throws up on the screen, again, something simple: refrigerant charge low, suggested action is to adjust refrigerant charge to, subcool of 10 degrees or something. A lot of what it does, these were experienced guys, so it was good to work with them because they had their own ideas, and most of what's programmed into them, a 20-year seasoned technician can figure out on his own usually. But what it was really good for, I think, was the less seasoned technicians, the ones that were just only in the field for a couple of years. They really liked it. It helped them diagnose units. They were also excited about using the analyzer, kind of raise the level of professionalism, of their craft. Okay, so this is just, heating performance, and that's an example of the fault screen that it puts up. Okay, so what did we end up finding in this case study? So I think out of the 30, we ended up only keeping 26 of them. Four weren't good candidates. And then of those, we split them up because we wanted to have a control group. So 18 of them we serviced, and 7 were not serviced, randomly picked by the technicians. And 1 of the units was replaced, which is another thing, and it's another thing that performance-based maintenance can do, is it can give you numbers to calculate, is it worth replacing this unit? So with this, we found that 1 unit was operating so poorly that the improvement of putting a new unit in would be economical, even though it wasn't dead yet. It's interesting that 4 of the 7 systems that were not given the extra service over the 1-year pilot had some sort of failure. Well, none of the 18 units that were serviced did. So we measured the energy efficiency as both EER, energy efficiency ratio, and calculated IEER, so we could compare it to the factory rating. And those were both improved by about 30% on average among the 18 units that were serviced. I don't have the chart here that shows how much each unit was improved, but there's quite a range. I mean, there's some units that were 50 or 60% improvement. There's some units that were only 5% improvement. And we saw the same thing at the other 3 sites that we did. So that means that you need to have a good sized population of units, because if you just do it on 1 or 2, you might not get the results that you're looking for. You need to have enough units where some of them have a big improvement where others may not. And it's hard to predict which ones are going to until you get into it and start doing it. So it's usually good to have a few units, like at least 10. Okay, the units that were not serviced over the year actually had a decrease in efficiency of 9% that we measured. And the 30% improvement equates to a restoration of about 2/3 of what was lost. So if we took the factory rating of the unit and then we measured what it was actually operating in the field several years later, we were able to recover 2/3 of that loss with this program. And then finally, the one unit that was replaced, I don't have that, but gave us a 57% improvement, which was enough to pay for that unit. Because oftentimes you wonder, is it worth, replacing this unit, or just let it run for a couple more years? So this is a way to calculate that. Okay, turning into dollars, projected annual savings based on cooling hours was about 20% for the savings for the units that were serviced. And then the ones that didn't get the servicing over the year was a 13% increase. So let's see, $33,000 a year energy savings among these units here. I mean, you can say that's about, $1,200 or $1,500 per year on average, which, is comparable to the cost of the technicians, 4 hours and some service costs. Roughly you get to keep half the savings, and about half of it is going to cost in terms of extra technician time. Okay, the reliability issue, I think, really stood out here. Of the 7 control systems that were not serviced, three failed, compressor failures, and 1 had emergency repairs. And none of the units that were serviced this way over that year had any kind of emergency failure. The example here is this 15-ton American Standard unit. It had a compressor failure because of low refrigerant charge, which normally the low pressure cutout switch would prevent that, but it also had a bad low pressure cutout switch. So the compressor ran with low refrigerant, overheated, and burned out. So the cost to replace the compressor and all that was a couple $1,000s. Had it been included in the performance-based maintenance program, this might have been caught earlier, and maybe spending only a few $100s in extra technician time would have prevented this. However, when we do the economics, we're not really counting this. We're just trying to do it on the energy savings because it's more of a hard number. Where the other one's like, you don't really know, is it going to fail? Is it not going to fail? Would it have failed if we didn't do this? There's a lot of ifs there, but just keep it in the back of your mind that it's pretty significant. And then the value, we tracked the actual implementation costs at this pilot, and then also tried to project implementation costs at 2 other locations and for different numbers of units in the program. So for the particular pilot, the total cost of training, labor, and materials was $73,000. So that gave us about a 2-year payback on the program. We estimated that with 40 hours of training, 2 analyzers, and 2 technicians at each unit for 4 hours once a year would give us a payback period of 6 to 10 months. Again, and also increasing the amount of units in the program to about 50 or 60, which for DoD is not a problem because they have hundreds of units, a couple hundred at each base. I don't know, most people might not have 50 or 60 DX equipment, depends how big your facility is. And then this is based on 12 tons average. So if you have, say, some fewer 30-ton units, that's also going to work. So okay, that was that. All right, so here's some of the comments. We sat down with the technicians after the program, got their feedback. These are comments from the facility director and the energy manager, actually, sorry. So one of them is the PBM training was a good skill booster. The 2 days were informative and useful, but the ability to get remote support online was most helpful. That's another thing that the diagnostic analyzer does. It's connected to cell connection. So when a technician is out at the site looking at the screen, not really sure what's causing the low performance or how to interpret it. I mean, I actually got calls a couple of times. I can pull that screen on their analyzer up on my screen on my desk and look at the same numbers they're looking at, and I can say, well, hey, looks like your high pressure is a little bit high and the evaporator pressure is a little low. Why don't you try this? So like an energy manager or a seasoned technician can assist them that way. And then I guess this second to the last one, that's where, again, they're talking about how to try to integrate it into their existing program. And they say PBM could be performed as part of the annual preventive maintenance service call, with the technician staying on the unit another hour or two on a 2 or 3 hour annual PM. So that seems like the most practical way to do it. And then also mentioned was to start the PBM on new units right away so you can track their loss of efficiency and performance. Okay, these are from the HVAC supervisor and technician themselves. PBM forces techs to take a deeper look at their systems beyond does it work, and the occupants aren't complaining. AC units look to be working okay, great visually. It's only when you connect the analyzer tool can you tell how much opportunity for improvement there is. And good to track performance and degradation of new units from the day they are installed. So we got really positive feedback here. The only thing that really shaded it again was the lack of resources. I mean, even though we had their technicians were doing this, the DoD was able to give them additional money for overtime and extra hours. So that money has got to come from somewhere to get it started. Unfortunately, it's got to, but once you get it started, then you have units that are failing less often and performing better, and then you can build on it. Yeah, kind of dig it out. But it sounds like you guys are doing a lot of this anyway.
Did the bays have the analyzer part of the tools?
Yeah.
They bought it?
No, we provided
Lease or something?
2 analyzers just as part of the program. Yeah.
That's part of the part.
Yeah. Okay. Do you guys want a microphone?
All right. So the question is, how often do the technicians have to come out to do the analyzation of the equipment?
For the pilot, we did it three times during the year.
Okay.
I think that it could be done twice, or even 1 PM and 1 checkup. We did it 3 times because we wanted to really track and measure what was happening over time.
And then a follow-up question, could you have that device installed permanently and you could get the live data readings?
You could do that, but
device,
then there's the cost of it. Yeah. Yeah, that's one of the reasons that was the force behind developing the analyzer, was that not all units have that level of instrumentation in them, even when they're connected to a BAS.
How much is that?
It's in the prototype stage, but it's probably going to be around $3,000 or $4,000. We're working with Refco and TPI now to try to get some manufacturing going.
Is your program, is it available to us, your presentation?
I think yes. I think it's going to be on the website, and I think also a video is going to be available.
Yeah, in like a week, you should get a week or 2, you get an email, and all the sessions you attended, and you should download handouts from those sessions that provided.
So, are there comparable sensors out there that, for potentially a fraction of the cost, you could install that would do a lot of this work?
That's tough.
Because the guy just asked, what if you put one on every unit?
Yeah, I mean,
that would be cost prohibitive. But what about sensors?
Okay, the power consumption, yeah, that's not too hard to measure. But even an actual RMS KW sensor is a few $100s. But measuring the cooling capacity, that is where you need quite a lot of sensors. and it's a difficult thing to measure. So the analyzer measures it both on the air side and on the refrigerant side. So for the air side, you need the inlet and outlet temperature, you need the static pressure across the coil, and you need the airflow. So that's a lot of sensors, some of which are pretty expensive. And then for the refrigerant side, you need pressure and temperature at the evaporator and the condenser. You got to do a lot of math to calculate the enthalpy, the heat content of the refrigerant, and then you need the refrigerant flow, the actual liquid flow in gallons per minute. Again, that's also kind of an expensive sensor. And it would be difficult to put all of that on an AC unit for any kind of a low cost. I mean, just think if the analyzer, I believe, has about $2,000 worth of parts and components in it, it's tough to justify adding $2,000 worth of sensors and stuff to a 10-ton unit. And maybe if it's a bigger unit, like a 30 or a 60-ton unit, yeah. I hope that answers. Yeah. Okay. Yeah, actually the temperature is their temperature humidity sensors. There's 3 of them. An experienced technician, somebody that's really can look at his gauges and his temperature reading, they make a couple other temperature readings, isn't really going to be able to give you an EER number, but he's going to have a really good seat of the pants feel of how well the unit is working and what he can do to improve it. So, it just really depends. It seems like, from what I've seen, most of the technicians at that level are nearing retirement, and the newer guys coming in, only have a few years experience and have a long way to go.
When do you think this unit will be available for
We're making prototypes now, but in really limited quantity. It's hard to say. It could be a year, several months to a year. Yeah.
Do you run any pilots in heating climates, and how do they work on heat pumps?
Yeah, Fort Irwin isn't really a heating climate, but it has about the same number of heating degree days as cooling degree days, about 3,000. And we did do it there, and we did do it in the heat pump mode. And yeah, it works the same way.
Similar percentage of savings?
It wasn't quite as much as with the cooling, if I remember, but still significant. And then we didn't do it in a heating dominated climate, because you're probably not going to have heat pumps in that situation. So usually in a heat pump application, there's going to be a significant number of cooling hours as well, because the heat pump, where they're applicable, is going to be sort of in the middle of the country, the temperate area. So when you add the heating savings and the cooling savings, that's what makes it look really good.
How did you get to this point with doing this prototype or this pilot study? Did you have to work with the Director of Public Works and the base ops contractor to do that?
Yeah, well, that's a good question. Okay, some of the some of the DoD bases have technicians that are government employees, Air Force or Navy employees. That was actually easier to do. We could work with the public work director, facilities director, and get their buy-in and put it on their workload. When you have a base that has a contracted, like a base contractor, that's more difficult, because their contract is written extremely tightly, and if you want to add to it, another 2 hours of technician time on each unit, it's a contract modification. It's huge. So at the end of the day, we weren't able to do it at bases that had contract. We may be able to approach that from the contractor's point of view. Those contracts usually go up for bid about every 3 to 5 years, and they may be able to offer that as an additional service and put it into their contract at the time of the renew. But it's just, we were told it was just, even if it saves $100,000, it's gonna easily be $100,000 worth of people's time to get the contract modified. It's hard to believe, but that's the government. Okay, well, thanks. Ending a little bit early here. Thanks very much. at the, glad you enjoyed it.